Good morning. Okay. For today's dependence question, let's use this one. It is a given function defined by summation of x and 1 over x. So this is really a rational function. So let's find the interval for which the function is increasing. The value, set a value for which f is increasing. So basically, we use the set coefficient to represent the increasing the value, the x value where the function is increasing. So let's try to find the increasing, decreasing behavior. As we talked about in section 3.3, the increasing, decreasing behavior function is determined by the first derivative. So you find the first derivative and set it equal to 0 or set it undefined, which means division by 0 and a lot of other situations. In this case, we have division, so we are looking for the point where the function is undefined and the point where the function is equal to 0. And those are the x values that allows us to divide up the entire number line. So you divide up the number line into several different intervals. So follow what we're talking about in section 3.3. Number 1, you find the derivative and find the point where the derivative is equal to 0. Or undefined, step 2, you will use the point that you find in step 1 and find the interval. So basically, we're looking at the entire number line, use those point as a cutting point or a separating point, partition point, which allows you to partition the entire number line into intervals, and then out of all those intervals that you find, you want to find on each interval whether it's increasing or decreasing. So that's basically like three steps calculation. So let's work out this question. Make sure we are recording. Figure out a routine that somehow works for you, like what kind of question, use what kind of method. Like this question is for increasing, decreasing. So first you have to find the derivative, set the derivative equal to 0, or try to figure out where the function is undefined. And those are x values. Once you find the x value, you want to find the interval. Once you got all your intervals set up, you want to figure out on each interval whether it's positive or negative, whether the derivative is positive or negative, which allows you to figure out increasing, decreasing interval. So you will find several intervals, and you want to label them as either increasing or decreasing. It cannot be both, of course, either increasing or decreasing. Right. Thank you. So we said we'll find the first derivative, find critical points. So find the derivative, 1 plus negative 1 over x squared. Doesn't look very good writing it this way. 1 minus 1 over x squared. So there are two types of critical points. One is when the derivative equals to 0. And for that, we have 1 minus 1 over x squared equal to 0. If that's the case, then 1 is equal to 1 over x squared. And for that, you then multiply both sides with x squared, then you have x squared equal to 1. And then you're going to have two solutions. X is either equal to 1 or negative 1. So there's two solutions. And this for the derivative equal to 0. Okay. And then we also have the derivative undefined. When it's undefined, you see there is division. Whenever you try to find an undefined point, it depends on how the function is being constructed. In this case, it's 1 minus 1 over x squared. So the undefined point is when you have division by 0. So x equal to 0 is the point. You have your solution? No. See, that's step 1. And let's look at step 2. For step 2, we want to find the intervals. We're using what we created in step 1 to set up the interval. Now, to find the interval, we draw the number line. Okay, on the number line, we will label the point that we find out in step 1. What are those points that we have? 0. But 0 is an undefined point. Undefined point is not part of the domain, so that's the division point. That we really are dividing up the entire graph into two completely separate graphs of the function. And we also have -1. We also have +1. So we got 3 points from step 1. Those 3 points separate the entire number line into the number lines from -infinity to +infinity. And you're like having the number line as a big stick. And then now you're making 3 cuts. 1, 2, 3. Cut the entire stick into 4 pieces after you make those 3 cuts. Now this 4 piece represents 4 intervals. So now we're able to find the interval. The first interval is from -infinity to -1. That's the first piece of the first part of the number line. And then we have -1 to 0. Then we have 0 to 1. And we have 1 to infinity. So those are the 4 intervals. We just want to find what was it increasing or decreasing on each interval. So step 3 is to ask yourself, now that we know the interval, is it on each interval, is it increasing or decreasing? That's the question. If the derivative is positive, then we know it's increasing. If the derivative is negative, then we know it's decreasing. So now it's down to the calculation of the derivative. So on each interval, we will label the increasing, decreasing. For example, the first interval. The first interval, you want to know if the derivative positive or negative, because that's what's telling us increasing or decreasing. So we're going to find the derivative value on this interval. So we're going to pick a point on the interval, let's say -2. Okay, derivative and -2 is part of the point for this interval. So you got 1 minus 1 over -2 squared. So it's 1 minus 1 over -2 squared is 4. And that looks like 3/4, which obviously is positive. So we know it's increasing on this interval. So that's for the first interval. You label it increasing. You can also draw on the graph just to indicate, hey, on this interval we got increasing here. I'm just using an up arrow to represent increasing, a down arrow to represent decreasing, so that the graph will visually represent the graph that you see in the graph of the function. Second interval is -1 to 0, and we're going to calculate the derivative on this interval. Let's pick -0.5. Right, and then you got 1 minus 1 over -0 squared, which is 0.25. So it's 1 minus 4, which gives you -3. You can also put it in the calculator. Now we know it's negative. And because it's negative, we know it's decreasing on this interval. So visually, it'll look like this. So it's going to decrease in here. Any questions so far? We do the same for all interval. I'm a little bit out of space, so let me finish step 3 over here. I have 2 more intervals. There are 4 intervals. So on the interval from 1 to 0 to 1. From 0 to 1, and then you want to find the derivative. You want to know if there is the negative or positive. You pick any testing point. Let's see, I pick 0.1. 0.1 is somewhere between 0 and 1. You plug in 0.1 to your function, and you have 1 minus 1 over 0.1 squared is 0.01. 1 divided 0.01 is 99. 1 minus 99 is -98, which is negative. And then we know it must be decreasing on this interval. Whenever derivative is negative, it's decreasing. So now we know that's decreasing, like this. Okay. And then so it's like decreasing. One more interval, the last interval is 1 to infinity. Let me try to draw infinity. All right, this interval, we don't know if it's increasing or decreasing. We're going to have to plug in a number. I'll put 2. So it's 1 minus 1 over 2 squared, which is 4, which then make it 3 over 4. So we know it's increasing on this interval. So visually, it should be increasing like this. Okay, so that's finished identifying increasing. Decreasing. You see there are 2 increasing intervals, this interval and this interval. There are 2 decreasing intervals. The 2 middle intervals are both decreasing. And realize that there's a vertical asymptote. So on here, my graph is not very accurate. So you probably should draw it this way. It should be like going down, but never cross the dashed line. The dashed line is at 0, 0 is on the fine point, so we would not be able to pass by. Unlike those 1 or negative 1 can actually connect it. For the dashed line, you can never connect. The 2 types of critical point really make a big difference. The one that's f prime equal to 0, the one that prime is on fine, and then realize that it's supposed to be different. You can also graph this on any grapher just to be clear what was the behavior of the function. But this is pretty much analyzing the decreasing behavior on the entire number. Any question? All right, let me record your solution. Thank you. Do you have any homework questions that you want to ask? Any questions from past homework? Questions? Okay. If there's no more questions, then move on to section 5, which is a summary of all the things that we did in chapter 3. So after chapter 3, we'll have another chapter test. It should be according to the schedule right after the break. Let's look at their calendar. I wonder if I can make it bigger. Oh. All right. Today is the 7th. Today is the 7th. All right, next week is the spring break. Yes, right? According to the schedule. So we're going to try to wrap up 3.5, and then we're going to start a little of 4.2. The test is after the break, so once we come back from the book, we're going to try to review chapter 3. So we're going to have a chapter test on the 23rd of this month. Any questions? So that's the plan, but we still have time but before the break and after the break. Just want to reaffirm our schedule. Okay, now today we're going to start with section 5. I'll let you know that our classes are now being recorded, so if you miss any class you want to review, they're online. The class recording is in, I label this class recording, is in the Clever Ultra website, and you don't see it immediately. This is the class running. If you want to see the recording, you have to go to the left under recording. And this is where you can see all the past recordings of class. So just want to mention that so you know it's there. And start with section 3, section 5. Chapter 3, section 5. Okay. 3.5 is called curve sketching. So when can you sketch the curve? Curve sketching will sound like a graph, a function. So when you try to graph a function, computer can graph function pretty accurately. If we want to graph the function by manually use all the knowledge that we know about the function, the accuracy definitely not going to be as high as what we can achieve with the computer graph. The curve sketching means, or sketching means you show the majority of the behavior function with the most important information from the curve. So we're not looking for 100% accuracy, we're looking for understanding the graph behavior, the overall structure of the function. So we're not trying to be 100% correct. So we are looking for, try to understand the function as much as possible using the first derivative and the second derivative that we learned. All right, so basically section 5 is combined all the stuff that we learned in chapter 3, try to utilize them as a way to provide information about the function. So here we are, and how do you do curve sketching? In general, number one, if you have a function represents a relation between the input and output. So we do want to find some basic things about a function. You gotta know the domain. Domain is the set of all the input value. So if the function itself has restrictions such as division, then you cannot have division by 0. That reduces the number in your domain. If the function has logarithm, then we cannot have logarithm of 0 or negative number. So that require us to have to focus on only positive input for logarithm. Similarly, with the root function, if your function f has root calculation, then you can only have square root of positive or 0. You cannot take square root of a negative number as long as you got a real function. So the step 1 is find the proper domain, which really depends on how the function is being defined. So that's kind of case-by-case scenario. Most functions, if you got polynomial, the domain is all real. If you have division, you want to make sure that the denominator is not 0. As far as domain, if you have logarithm, you want to make sure logarithm only have positive input. That's the most common scenario. All right, step 2. We're going to find critical values, critical points, and this is solved by first derivative. So you find the first derivative, set it equal to 0, or undefined, and you find a critical point. Number 3, you want to find possible inflection, which determined by the second derivative. So you find the second derivative, set that one equal to 0, or undefined, not give you the inflection point. So basically, we find out those necessary points, and we try to mark them on the number line. Number 4, we also want to find the reversible asymptote of the function, which is like division by 0 for a simplified rational function or fraction, simplified a fraction. You make sure the denominator is not 0. Whenever the denominator equals to 0, we have a vertical asymptote. We want to mark that out on the number line also. So the critical point, inflection point, and asymptote, they were supposed to be marked out on your number line, so you'll be sure that how is your number line look like. So you kind of combine section 3, section 4, and section 1. All right, number 5, we consider the function's limit if the x value is really, really large. And that's trying to identify horizontal asymptote. So step 4, you want to determine vertical asymptote. Step 5, you're going to find when x goes to negative infinity or positive infinity, which really means when x goes to negative infinity, we're looking for the far left behavior. And if x goes to positive infinity, you look at far right of your entire xy plane. You want to look at the right side behavior of your function. So right and left behavior of the function, vertical asymptote of the function, and vertical asymptote, horizontal asymptote, those are the increasing and decreasing behavior and concavity. All right, with all that, you know, create the proper number line, mark out all the critical point, all the inflection point, the vertical asymptote. All right, and then you want to determine the into where it's increasing, decreasing, or concave up, concave down. So it sounds like a whole lot of work, which you probably have to do the same thing that we did in section 3, the same thing we did in section 2, maybe a few calculations of the asymptote if we have any. Number 7, we want to find the value of the y value, and then you want to draw the graph. And if you want to draw the graph, you need xy pairs. So the previous 6 steps only tells you the x value. So now the last step we want to be able to calculate the y value, and therefore we identify the height of the function and we sketch the graph. Any questions? So let's try an example just to see how to sketch a function. So here, we're going to use those key ideas or those steps, 7 steps. Sounded like a whole lot. All right, but we didn't really utilize a lot of stuff. You have a function, you find first derivative and the second derivative, and you determine the increasing, decreasing, and concavity. Together with that, you want to find the height of the function, which is normally determined by the y value of those key points. Let's see, first the sketching steps. So let's try to follow those 5 steps. Okay, so we're going to try to follow the 7 steps, which is being mentioned here. Right, step 1, we're going to find the domain, and that should be pretty quick since we have a polynomial. So the domain is all real, so one domain is all real numbers. Right, you draw the entire number line and get ready for increasing the decreasing behavior. And then we got step 2, there you find a critical point. You know, to find a critical point, you want to find the derivative. So to critical point, find critical points. All right, to find a critical point, we need the derivative. So this function, what's the derivative?
9x squared minus 20x plus 7.
Squared minus 20x plus 7. Okay. We aim at finding the critical point. There are 2 types of critical points. The derivative is equal to 0 or the derivative is undefined. And here is polynomial, always defined. So we're going to set equal to 0. That's the only critical point we will have. Okay. So now it's time to try to find the solution for this. So is it possible to factor this? If we can factor it, will save us a lot of time. For the 9x is 3x times 3x. All right, for the 7, there's only 7 and 1. There's no other factoring. This does not work well. Right, you have 21 and 3. That does not work out. Well, but we could change this 3x to 9x times x. Maybe that factoring is a little bit better. So we're going to change our factoring of the 9x squared. 9x squared can also be 9x times x. I'll change here to 9. This is 1, 9x times x. And that makes 7x and 9x, right? So that doesn't work out. So maybe we can switch this. We got 9 here, but 1x over here. That still doesn't work out. So does that mean it doesn't factor out?
Complete the square.
Oh, the perfect square over there. I'm gonna do quadratic formula since it looks like it's not going anywhere with the factoring. All right, so let's try to find the solution of the equation with quadratic formula. So x is equal to, the numerator is negative b plus or minus root of b squared minus 4ac. Negative b is 20, and then we have plus or minus root of b squared, 20 squared is 400. B squared minus 4 times a times c, right? B squared minus 4ac. This is over 2a. That makes it 18. Fraction negative b plus or minus root of b squared minus 4ac, right? All right, let's use some calculator to see if that works out. So 400 minus 4ac 148 equal to 20 plus or minus root of 148.
237.
You have a different one?
What's the simplified?
Oh,
Yeah.
148 after simplified.
Yeah.
Okay. Four, 9, 7, 36 and 7. Okay. So this has, how do you simplify it?
2 root 37.
2 root 37. So this is equal to 20 plus or minus 2 root 37. Let's do it and factor out. Every factor has a coefficient that's even number, so we divide it by 2. Then we have this divided by 2 is 9, this divided by 2 is 10, this divided by 2, the 2 is gone, so we have root of 37. Okay, so far? So that's the critical point. Then that's the, okay, now very easy. We can also double check if I find the right number. Just want to make sure we're not making any mistakes. So here's our function, y is equal to 3x cubed minus 10x squared minus 10x squared and plus 7 plus 5. So here, that's the critical point. So critical point is when the function stop increasing and start decreasing, or stop decreasing and start increasing. So those are the critical points. We can double check if it's the right number. We're going to pop this into a calculator. The two number that we find out is 10 minus root of 37 over 9, and then the 10 plus root of 37 over 9. So we can actually see what that value is by to a calculator. So it's 10 minus square root 37 over 9, which is the 435 we have. So that's the first critical point, this one. The other critical point should be when it's plus. We find, see the value here. It's roughly 1.787 is the same thing as we did for this. All right. So basically, we know this is roughly 0.435, and this is roughly 1.787. The decimal, this is the accurate solution, but the decimal made it easy for us to mark it out on a number line, so we have to kind of see it. So that's our step 2. We can actually graph it for increasing, decreasing. But step 2, we're supposed to find a critical point. That's done. And step 3 was find the inflection point. So we're going to move on to the next step. Now we find the inflection point. So you find the inflection point, or point of inflection. All right. To do that, we need the second derivative. So we're going to find second derivative, which is second derivative.
18x minus 20.
Okay. So we're going to set this equal to 0 just to find the inflection point. Okay. And that's degree 1, so it made it easy to solve for it. And you realize, and you have x equal to 20 divided by 9, 20 divided by 18, or 10/9. And that should remind you something. I mean, you see the critical point, 10/9 minus root of 37/9. This is 10/9 plus root of 37/9. So this point is really below that and higher than this. Really, it's a midpoint. So if you look at the graph that we just drawn, you don't have to draw the graph, but the graph really says a lot of things. Just right in the middle, 10/9. It's right in the middle of these 2 points. We can actually, right, yeah. We can really try to find the decimal point. Like 1.111 repeated. That's the inflection point. Any questions? All right, so substitute. Now, what do we do next is try to find if we have any vertical asymptote in this case. Vertical asymptotes, I'm just writing VA. Any vertical asymptotes, that's when you have a rational function where the denominator equal to 0, right? In this case, there's no vertical asymptotes. We don't have any. Step 4, step 5, and let's try to find horizontal asymptotes. If x goes to infinity, or x goes to negative infinity, what would the y value? To find the limit of those functions. In this case, we're looking for left and right behavior and right behavior. All right, it looks like the limit of this function when x is really, really large, say limit of f of x, if x goes to negative infinity. And this we have talked about it before. If you have polynomial, the behavior of the polynomial is determined at infinity. It's determined by the highest degree. So the limit of this function, even though you have a big polynomial, this is the only thing that actually matters as far as infinity or the left and right. It's 3x cubed. That's the one we're looking for. X goes to negative infinity, and we're looking for this limit. Do you know what's that limit? Negative infinity, because x is negative infinity means negative is larger number, right? So x is a negative large number, cube of a negative large number is still a negative large number, so the entire thing is a negative large number, which we represent as negative infinity. All right, we do the same for the right side behavior. On the right side of x, and x goes to positive infinity, is still determined by the highest degree. So its limit is 3x cubed. X goes to infinity. X is a large positive number, so 3x cubed is also a large positive number. So that's what's going on. So on the left, it's going down. Negative infinity says it goes down on the left, and on the right, it's in positive infinity, so it goes up. And you see the same thing when you look at the actual graph. Left is going down, on the right side it goes up. So that's all there is. So really we're gonna try to find out where is increasing, where is balancing, this concave down, concave up, and then that's increasing, and then it goes all the way up, and here it goes all the way down. So even though we are already seeing the graph, we try to graph this actually, but in the curve sketching we don't have the computer, but you want to understand the behavior function just by looking at all the derivative that we had on our hand. So now that's 1, 2, 3, 4, 5. Any questions? All right, so starting with step 6, we're going to try to get ready for graphing, but I realize I don't have a lot of space. So I'll write step 6 over here. It says for us to draw the entire number line and then start getting ready. So step 6, we're trying to label the x value of the graph. Step 7, we're going to calculate the y value and start drawing the little point on the graph. Okay, so here, if you want to draw a number line, it's our x value. On the x value, we're going to label So first we know the left and right behavior. We know it's negative infinity to positive infinity. And we also know that this is like a, I guess I should label it a little bit better, but I did the curve sketching. So this is 0.435 about the increasing behavior, and this is 1.787. Right in the middle of these two, we got the 10/9. These are the inflection points. If there are other things that we need to watch out for is that this function, if x equal to 0, the value is 5. So that's also something we should watch out for. Theoretically speaking, we should also set this equal to 0 and find the x-intercept. You know, the 0, 5 is the y-intercept, but it will also have x value that causes the y equal to 0, so that should be the x value. But we're going to try to graph the majority of this. So in here, what I'm drawing in that number line is everything that we had so far about the x value. Now 7 is asking us to really find, we need to draw the graph, so we need points. In order to get a point ready, we need to find out what was the x value for each, what was that y value for each x value we already labeled, and that really need computation. Okay, so f of 0.435 is equal to, we're going to pop this into a calculator and figure out the point. We know f of 0 equal to 5. That's something pretty easy to draw. And we also want to find out f of 1.787. And that needs to be calculated. And f of 10/9. So for all the value that you label on your number line, in step 7, we're supposed to find the y value and draw the point to finish the first sketch. Are we okay so far? All right. I really need to pop this into a calculator.
First one was about 6.4.
Okay, thank you. 6.4. All right, and what about this one? All right. I guess I might have posted a couple of online calculators just to help us. All right.
Okay, second one is about 4.55.
Okay. 4.55. Okay.
No, that one's for 10/9.
Oh, this one's for the
Yeah.
10/9. Thank you. I'm going to draw the y-axis.
Okay, 1.787 is 2.7.
2.7. So with all these points, we can start briefly sketching it. The 0, 5, this is our x-axis. I have points 4, 3, 5, so I'm guessing the y-axis is over here. This is our y-axis, and 0, 5 is on the graph. So let's assume this is the 5, and this is the 10. I mean, sketching, I can't be that accurate, but I see at least want to show the overall tendency. So that's our 0, 5. And this one is a little bit higher than the 5, so 6.4, which is kind of like this, 6.4. And then for 2.7, for this one we have 4.55. So it went a little bit down, 4.55. It's a little bit lower than the 5 there. So it went increasing and then decreasing. I mean, this is a local maximum, as you know. It's one of the, it's like increasing, then decreasing. Those are the two critical points, and then increasing. So that's the critical point behavior. increasing, decreasing behavior. And then for the third point, this one, we have 0.7. So when like halfway between 0 and 5, over here, 2.7. So this is the inflection point. So it's concave down, and then concave up, and this is all concave down. So this is a sketch graph. So in this sketch graph, you were supposed to show increasing, decreasing, and increasing. You are supposed to show concave down, and then concave up. So that's the inflection point. Inflection point is up to the concavity, different concavity. And then we also have the overall, at left side it goes down, and the right side it goes up, and this is a rough sketching of the curve. Any questions?
How do you tell the concavity from the second to the?
Oh, we were supposed to do what we were talking about in section 4. We would plug in a number set. See, below 10.9, we have such as 1. So if you plug in 1, 18 times 1 minus 20, it's negative. So we know below 10.9, this is a 10.9. To the left of 10.9, they're negative. To the right of 10.9, you can take like 2, actually equal to 2. And 18 times 2 minus 20 obviously positive, which means to the right of 10.9, it's supposed to be concave up. To the left is concave up.
Okay.
Kind of like with here, we were supposed to plug a number to understand increasing, decreasing. For example, 0.45, 435 is the separating point. It's supposed to create 1, 2, 3 intervals. I didn't exactly do it because that was a lengthy process. But you can still double check. Say below 0.435, you have 0. You plug in 0 here, 0, 0, and then you have 7. Obviously, it's positive, so it's increasing to the left of 435. Right between the 0.435 and 1.777, we have 1. And you can plug in 1, so 9 minus 20 plus 7. Plugging 1 is obviously negative, so we know it's decreasing right between these 2 points. And above this 1.787, you can hit 2, and then you can plug in the 2, you can see 8 times 36 minus 40 plus 7, which is positive, so we know it's increasing on the right of the last critical point. So to determine increasing, decreasing, we really have to know whether the derivative is positive or negative. So finding the critical point may not be sufficient, but it does give you a separate point. Any questions? All right, so this is still a short version of all we're doing. In section 3, we have detailed analysis of entire number line, whether it's increasing or decreasing. In 3.4, we have pretty detailed understanding of the concavity. Once you find the inflection point allows you to separate from concave up to concave down, and that's separating point because at the inflection point it equals to 0 on the line. In this curve sketching, we just try to find some basic points, and then we calculate those values. So even if you don't remember the concavity or increasing, decreasing, just by following to 1, 2, 3, that tends to give you an overall behavior. We know the left is going down, so down, and then 5, and then 6.4, and 2.7, and then up. So just by the information that we already have in the previous 5 steps should give us some general idea of what's going on. The sketching there is not accurate, but what it does is bring information of what was the major,
the trend.
Yeah, the trend. And that's why it's called sketching, not graphing. Graphing should be a little bit more accurate than this. Any questions? This is a practice on curve sketching. And let's finish the 7 step. A little bit messy, but it's the idea. All right, so this is a solution provided in the book. So you know the domain of the entire real line, find the derivatives, set the derivative equal to 0. We got those two. 0.435, 1.7. Exactly. You can also calculate decimal or the formula. The formula itself does not allow you to mark it on a number line, so we definitely have to try to find the decimal point. And then we're going to find the inflection point, also make it decimal, just so we can mark it on the number line. There's no multiple asymptotes since there's really no division at all. And then this is the behavior at infinity. And then we graph the function. And now we say mark all those on the number line. Oh, we could separate the entire number line into 4 different intervals. On each interval, we can identify increasing, decreasing, identify contivity, and then start sketching it. 7, we use all those points that we get. The point that we get only allows you to draw like this line segment, but then you try to smooth it out with contivity. And that's what we have here. See, this one has no contivity, but once you know it's supposed to concave down, and then concave up, concave up, yeah, smooth it out with the curves. Any questions? Another curve sketching example. All right, let's look at a couple examples from the homework. Do you guys have any homework questions? I know you two. All right. Let's see. It's a little curve sketching is really hard to test on our online homework because you cannot draw it. Yes. So what it does really are retesting all the stuff that we already had in 3-4, in section 3 and 4. So let's look at the question that we had. So I feel like redoing a lot of homework that we had in the previous section with a little bit combined. We want to find the increasing, decreasing. We also want to find the contivity. So kind of like everything all put it in the big pot and mix it up. So you see occasionally an increasing, decreasing question pops out, and then there an inflection point pops out, and then there are contivity. So you're going to have to keep in mind that this time, do I use first derivative or second derivative, depending on the question. Just keep in mind the increasing, decreasing, you're going to use first derivative, but contivity, you have to use second derivative. Right, over here, consider this function as degree 3. Kind of similar to the example that we just did. For this, we want to find interval, 3 interval, where A and B are the critical points. So this step 1, we want to find the critical point because A and B is supposed to be the critical point. And obviously, using the critical point, we can separate the entire number line into 3 intervals. So we know we were supposed to find 2 critical points. Once we find the critical point here, we want to use the increasing, decreasing. So on the interval 1, 2, 3 interval. Each interval you're gonna label whether it's increasing or decreasing. I feel like this could be part of the 3.3 homework. And then I'm gonna move on to inflection point. The inflection point and separate the entire number line into 2 intervals. On each interval you're gonna identify contivity. So pretty much a combination of 3, 4, 2, 3. Any questions? 2, we probably would do the same thing as we did in the example. I'll skip that one because it's really similar to what we just did. Second question. All right. Second question is slightly different because in the example that we just did, it was a polynomial. It's a polynomial, and then this should be almost identical to what we did in here. Well, I could use this one as example, and then I'll move on to the other question. All right, I realize that this is a bit messy, so maybe work on the first question on the homework will make it a little bit slightly more organized. All right, so the way the question is being asked could make us organize our thoughts, try to trim our ideas. Okay. So here we were given a degree 3 polynomial, and our goal is to find out the interval where it's increasing or decreasing, and the interval where it's concave up, concave down. All right, so we're going to start with the increasing, decreasing. We find a critical point, and then we're going to study increasing, decreasing. All right, so for that, for both of these, you need first derivative. So we're going to first calculate the derivative, and which is
negative 6x squared plus 72x minus 150.
So can we set this equal to 0? All right, can we solve this? Is there any way we could simplify this?
Can we factor out the 6?
We divide all the coefficients by 6. And then we have negative x squared. Divide this by 6. Divide this by 6, what do we have?
12.
12. And then last one divided by 6?
27.
27. 3 and 9. Okay. So let's see if it works out. So negative x. And then x. So negative x times x is negative x squared. 3 and 9. One of them has to be negative though, right? Because it's a negative 27. So which one should be negative? 3. Because we want a positive 12. So this is a positive 9x. So that has to be positive 3x. So we would have negative in here. We must have a positive in here. So this one works out for factoring. Are we okay so far? So what was the solution? Negative x plus 9 equal to 0, so x equal to 9. Now x minus 3 equal to 0, then x equal to 3. So that's the 2 solution. Again, with this 2 solution, we then draw the number line. On the number line, you will label small number first, and then big critical point over there. And know that the left endpoint is negative infinity, the right endpoint of the number line is positive infinity. So we're making 2 cuts, and those are going to be the A and B, right? So we will have 4 interval negative infinity to 3, 3 to 9, and then 9 to 4 infinity. So this must be the A must be the 3, right? The B must be the 9. So those are the critical, and then we find out, and then over here is the 4 interval that we can see. 1, 2, 3 intervals. 1, 2, 3 intervals that we have. So the negative infinity to A is really the negative infinity to 3. 3 to 9, 9 to positive infinity. Each interval, we really want to know the increasing and decreasing. If you want to know increasing and decreasing, you have to test the derivative value, right? So for example, the first one, let's pick a number. So you want to find the derivative at, what's below 3? 0? I think 0 is quicker. So derivative at 0, what is it? Negative 162, which is negative. So we know it is decreasing. So over here is decreasing. Now, the second interval we can find the derivative at like 4. It's still going to be too hard, a little hard to calculate. So what we can do is, this is factor out of 6, right? The 6 does not factor value. We can plug into the factor form. So you can plug in 4 in here, which made it positive, right? You can plug in 4 here, which also made it positive. So the entire thing should be positive. Of course, you should multiply 6, but 6 really doesn't change the value. So even though we don't know the value, we know it's definitely positive. So it's increasing. So if you want to draw the graph, so it's decreasing, then increasing, right? I'm guessing then decreasing because there's no more factor. So we know it's increasing and increasing, and over here it must be decreasing. If you want to confirm, you can calculate, 10, f prime at 10. So if you plug in negative 10, well, I should use a different color just not to mess it up. So it's negative 10 plus 9, which is negative, right? And it's negative 10 minus 3, which also is negative. So you have negative number times negative number, which make a positive number.
No, it's the second one should be just 10. 10 minus 3.
Oh, it's 10 minus 3. Yeah, you're right, you're right. Negative 10 is from the negative x, and there's no negative in this one. You're right. So that's positive 7, and this is the negative 1, which will make it negative. All right, so the value would be, this is 7, negative 7, so it's decreasing. Negative 7 times negative 6, which make it negative 42, actually, if we have to calculate f of 4, f of 10. You can plug in this one to know what it is, but it's a lengthier process, so I plug in this one just to show you quicker. Alright, so we know that's decreasing. This ends up with a rough sketch of the increasing decreasing figure. So you can know that now it's going to be this way. And right in the middle of 3 and 9, there should be an inflection point where I think you go concave up, then concave down, and here should be an inflection point. So we were supposed to find the inflection point, and then for the inflection point, we normally find it out from the second derivative. All right, what was the second derivative again?
Would be negative 12x plus 72.
Plus 72. We set this equal to 0, so x equal to, now we can move it over, right? Move to 12x equal to 72, so, which is 6. So now the c equal to 6. And of course, we want to know concavity. I can almost guess that this is concave up, then this concave down. So I think it's CU and then CD. We can always double check. You can plug in below 6, you can plug in 0, which is 72, which definitely make it concave up. Above 6, that makes 7. So negative 12 times 7 plus 72. That's negative 84 plus 72 is negative. So we know it's concave down here because the negative second derivative concave up, concave down. So up, then down. So this must be CU, and this must be CD. This was 6, and that was 3 and 9. We got decreasing, increasing, and then decreasing. Let's finish all the solution that we just did. Any questions? So this is slightly more modeled example where the solution seems to be integers. The one on the textbook, and that one was a little bit irregular because we had a solution that is, you have to solve with quadratic formula, and they were decimal answers. That's not so easy to mark out on the graph. Okay, so this is the first example. I also want to go to the second example so you can start it. The second example does not have polynomial, which makes it a new situation. It is an exponential function, but exponential function actually has its nice feature in a way that exponential e to any power is positive, which means the entire thing is a positive number. When you try to differentiate the derivative exponential function, it has itself as a part of the factor. So that really limits the complexity of some function itself. So you can always differentiate with exponential differentiation. It's going to be exponential function multiplied by a little factor. And that factor, depending on the power here, it won't go as high as the degree 2. So I think it should be okay. So degree 2 is the highest degree we can get out of the factor. So we're going to try this one. So you can model your solution with the solution that we had here. And this is our section 3.5, number 1. Let's try 3.5, number 2. Again, we're going to try to use the first derivative to derive the increasing, decreasing, or maximum, local minimum, and we're going to use second derivative for inflection point and concavity. Okay, so we're going to do derivative. Okay, So we're gonna start with the relative max and relative mean. You know they were supposed to be when it's increasing and then decreasing, then you have maximum. When it's decreasing, then increasing, and you have minimum. Decreasing, increasing to get a minimum. So the minimum or maximum determined is related to increasing, decreasing. So to study increasing, decreasing, we're gonna find the derivative, which is what's the derivative of this?
E to the negative 3x, right?
Exponential function, so e to the negative 3x squared. Exponential function derivative is itself. And then, I mean, chain rule, right?
Right, negative 6x.
So we have to multiply this by negative 6x. Okay, so this function should tell us increasing or decreasing. This function, to find a critical point or to find increasing, decreasing, you would have to find a critical point, right? So for the critical point, you would set it to 0, right? Because it's differentiated everywhere, so we don't have any undefined point. To find critical points, let's f prime equal to 0. We're going to make this equal to 0, but this is multiplication, right?
Mm-hmm.
If you want to make this one equal to 0, then we know the exponential function, this one, it will never equal to 0 because e to anything is positive number. So this is always e to the negative 3x squared. It is always positive. It will never ever equal to 0. So the only chance for it to equal to 0 is this. So to make it equal to 0, we'll have to make the negative 6x equal to 0. So the solution is 0. So x equal to 0. All right, then we're going to use 0 to separate our number line. And remember, critical point is not your maximum mean. It is giving your interval to allow you to study the maximum mean. So right here we have a 0, right? Yeah, 0. So then we have negative infinity to 0 is one interval, 0 to positive infinity is another 0. So we get two interval, and then 0 to positive infinity. Each interval we want to know if it's increasing or decreasing, right? To understand increasing, decreasing, you have to use your derivative. So we're going to look at the derivative. The first interval, you're going to pick a point on the interval, like
1.
Negative, right?
-1.
Negative 1. So you go negative 1. And what is it?
It'll be increasing.
It's e to the negative 1 times negative 3, e to the negative 3, and then negative 6 times negative 1. So it's positive. So it's e to the negative 3. Negative 1 squared is 1 times 6. 6 times negative, positive 6, which is positive. So we know the function is increasing. Increasing. So here, it's increasing. And then the second interval, on this interval, let's try to find a point, such as 1. So the value would be e to the negative 3 also, times negative times 1. That makes it negative, right? It's multiplying a negative number, which then makes the decreasing goes down, right? So the function goes increasing, then decreasing. So it definitely have a local, right, between the increasing and decreasing. This is a maximum, right? Here. Increasing, then decreasing. Of course, right in the middle is connected. We're going to make sure there's no break. If there's an asymptote, we will not have a maximum. But the entire thing is continuous at 0. So you have to have you're not allowed to make any jump. You have to allow a maximum point and then start decreasing. So we know at 0, we have local maximum, a relative maximum at x equal to 0. Relative minimum, we don't have any minimum, and this is none. The only thing that we had is 0, and 0 is obviously a local maximum point. There. Any questions? That should be it, right? So then we have the inflection point. We're looking for inflection points. Oh, it says write D and E if any of them does not exist. So we would write D and E instead. So here it's D and E. Okay. For inflection point, we need to find the second derivative.
Negative 3x squared times negative 6x.
The second derivative is the derivative of the first derivative. The first derivative is the multiplication, so the second derivative we have the product rule. Because you get an x there, you got x there, it's a multiplication of two functions that have x, so we need to do the product rule. So let's do product rule. We're gonna keep the e to the negative 3x squared and find the derivative of negative 6x, which is negative 6, right? That's the first product. Plus, this time we're going to keep the negative 6x, but we're going to differentiate the e to the negative 3x squared, right? Which then have to have itself as derivative, you're going to multiply another negative 6x. Because that's how it is, the chain rule, right? If you're differentiating this, then you're going to end up having one more of this. It's a chain rule. And that's the second derivative. It's pretty long. Are you okay so far? So what we're going to do is remember that we have exponential function in all of them. So what we can do is combine terms and then factor out common factor. So here are the algebra. The first one, as a tradition, we move the negative 6 to in front of the e exponential notation. So you have negative 6 e to the negative 3x squared. For the second one, we have negative 6x times negative 6x, which is positive 36x. So after we combine them, it will be plus positive 36x squared. And then we have the factor e to the negative 3x squared. Are we okay? All right, so this is about the thing about exponential function differentiation. You always have e to that thing in there, and it will never change form, right? You may have other stuff that you keep multiplying it, but every time you differentiate, you're not allowed to change anything in there. You want to multiply the inside function, and because they're extra term, the derivative gets more and more, because in the next step, you have to, like, if you're trying to find third derivative, which we're not doing, but if you're trying to find third derivative, it's going to be even more than this, right? So, and that was like e to the negative 3x equal 1. But here, you factor e to the negative 3x, right? You can see, so it's move up to degree 2, and you can almost imagine in the third derivative, you have the same thing, but multiplied even higher degree of polynomial. It's kind of the thing about differentiation, the more you differentiate, sometimes the level of complexity increase. So this is equal to, we got factor out the common factor exponential parts. So everything else without the exponent is this, e to the negative 3x squared. Okay, right? To find the inflection point, we'll set this equal to 0. Because it is well defined for any x value, we don't have any undefined points, so the only way for it to have critical inflection point. We set the derivative equal to 0. Again, we talked about this. If we know this function, it is always positive, so that it's impossible to make it 0. So the only part that make this multiplication equal to 0 is this. So then, yeah, so we have negative 6 plus 36x.
It's x squared.
There's a square, x squared equal to 0. Then you can solve for the x squared. So x squared, you move the 6 over, right? Plus 6 plus 6, the x squared equal to 1 over 6. So x equal to plus or minus root of 1 over 6, right? You're going to take square root is degree 2, so you're going to find 2 of them. So it's negative root of 1 over 6. And then this is a positive root of 1 over 6. That ends this question. Any questions? Are we okay there? So we can imagine that right in the middle we have a 0, and then we add 2 more points. I don't want to draw another number line. So they're actually symmetrical. You get here you get positive 1 over root 6, and here you get negative 1 over root of 1 over 6. And you may want to study the concavity. So below the negative root of 1 over 6, I take even more negative, right? You take negative 1. So if x equals negative 1, so it's negative 6 plus 36, positive. And then this is also positive, so it's concave up. So below the negative, this is concave up. Between the root of negative root of 1 over 6 and positive, it's right between these two we have 0. So you plug in 0 to your second derivative, you got 0. So it's negative 6 times the positive. So it's negative, so you can see it's concave down in here. So it's increasing, but it's a concave up increasing, and then it starts concave down. It's like increasing and concave down, and then decreasing concave down. And right back here starts concave up again. You can also plug in numbers, see x equal to 1, which is positive, or 5. This is 5. This entire thing is positive. That's already positive. So this is concave up. So it's concave up, concave down, concave up. That's the concavity. We're not required to do that, but it's once you find the inflection point, the rest will know the value of the second derivative. Any questions? All right, so that's the answer to this one. And let's enter this. We does not have a local minimum. We have a maximum as 0. We have a negative square root of 1 over 6. And then we have a positive square root of 1 over 6 for the inflection point. So that's the solution for the second question. That should end up with our second example. I hope at least you should start with these 2 questions. And then let's try to get ready for the second test, which is the week after the break. That's Thursday after the break. Okay. This is today's attendance question. We did this one, and that should be it for today. So section 5. And just remember, it's a combination of all what we did, but there's really not much new stuff in this section. Except a little bit graphing practice to try to be more hands-on. I mean, it's kind of the thing with graphing. The more you draw, the better you add it. So, I mean, I don't know if you guys have art classes or drawing classes in high school and middle school. And that's the thing that the more you draw, the better you get it. All right, that's it for today. Thank you. That's all right, too. Let me save this and show you our solution. We did this one together. I think that's the one. So you would define the derivative right here. And once you find the derivative, it's this. Like derivative, and you set equal to 0, which ends up giving you -1 and +1. The undefined point, then you have 0, so you have undefined point, the -1, +1. Now you have 1, 2, 3, 4, 4 intervals. Each interval you're going to try to plug in some number, just so you would know if it's increasing or decreasing. And that's pretty much the picture. That's right. I mean, when you look at the drawing, you should know the increasing and decreasing. It's kind of
Only when it's
key.
increasing.
Yeah. Okay. You can also look in this one. And this posting it online, so if you are wanted to double check today's working, you can always look it up. I also recorded the class session.
Okay,
If you want to.
thank you.
You're welcome.